Okay, thank you for coming in such a big number. And you're probably all waiting for Christoph to start his talk, so I'm just going to let him do that.
Okay, thank you. So, hello, good morning everyone. My name is Krzysztof Opasiak. For some non-Polish speakers, I know it may be hard, so Chris is really good enough. I work for Samsung R&D Institute Poland, and in my daily job I deal with USB support in Tizen operating system. Apart from working for Samsung, I'm also doing my PhD degree on Warsaw University of Technology. I'm also working with USB-related research, but I cannot talk about them now. So, now let's go through debugging and our USB devices and drivers. First of all, the schedule. In the beginning, I'm going to give you some overview of the USB basics. For those of you who attended my talk last year, those slides may look quite familiar, but for those of you who didn't attend, we have to repeat this. Then we will go to plug-and-play philosophy and how it works in Linux. And then we will start debugging and getting what we really want, not what kernel offers. So we are going to talk about how to force kernel to do what we really want, not what it thinks we want. Then we will try to get something more from our kernel. We will try to sniff the communication between drivers and between our USB devices. Short summary and Q&A session in the end. Okay, so we have to verify if you are in the correct room. This talk is not going to be about kernel debugging in general. I'm not going to show how to use KGDB or stuff like this. This is USB-related talk, so now is the time to change the room if you're in the wrong one. And I'm also not going to give you a cure for all your USB problems. Sorry, I'm not a god, I cannot do this. I will only show the techniques which can be used to fix some common problems which you can, they're all around here. Okay, the USB basics. First of all, let's think what USB is about. Many people say that USB is more a network than a bus. Because USB is about the same thing as the internet. It's about providing and using a service. Of course, a little bit different kind of service. But we have also cloud printing and cloud storage, all that kind we know from the internet. In USB, we also have it. The design is a little bit different than in internet. In internet, we have well-known architecture client-server. Yep, so everyone knows it from studies. And in USB, we have the host and the device. The USB host is a machine which is being extended with some additional functionalities, some additional services provided by the device. Device is a slave in this design. Single device may offer multiple functionalities to the host. Single host may use multiple devices in the same time, but single device may be used only by one host. In the same time, of course. Okay, some basic entities from the USB world. In TCP/IP, we have the abstraction of ports, the destination of the source. In USB, we have endpoints. It's a little bit equivalent, but there are some differences. First of all, there is much less of them. Only 31 endpoints, including endpoint 0. Endpoint 0 is a little bit special, because as the only one, it can transfer the data in both directions. Ports in TCP/IP were bidirectional. Endpoints are unidirectional. Only endpoint 0 may transfer data in both directions. If we are talking about the directions, USB bus itself is a host-centric bus. It means that host is a master on the bus. So even the directions are taken from host perspective. So if we are talking about the in-transfer, the incoming transfer, it means that we are transferring the data from the device to the host. And if we are talking about out transfer, we are transferring the data from host to the device. Okay, That's the basic stuff. Now, how those endpoints fit together into device? Well, maybe endpoint types before that would be better. We have in internet, we have TCP and UDP. That's the base protocol we are using every day. In USB, we have 4 types of transport. First of them is control 1. It's the only one which uses the bidirectional endpoint, so it's reserved for endpoint 0. It's the only one which is mandatory for device to implement. So each device needs to have endpoint 0 and support the control transfer. Another one is the interrupt. It's used to transfer a small amount of time-sensitive data. Those kind of transfer reserve some bandwidth on the bus, so you can connect only a limited number of them. Another one, the most popular, it's bulk. It's used to transfer large amount of data, which is not time sensitive. So we have a huge package of data, and you say, okay, when the bus is free, just send this, I don't care, notify me when it will be ready. The next one is ISO. It can transfer a large amount of time-sensitive data, but it does not guarantee the delivery. So you just send the data, and you don't know if it has been delivered or not. We use this transfer, well, when it is better to drop a frame than hold the whole stream and force the retransmission. So video. Generally, video. It's like UDP. You are streaming the video and you don't care about the frames from the past. Okay, so the USB device layout from the logical point of view. So device may have multiple endpoints. Endpoints are grouped into interfaces. Interface is a group of endpoints which is used to implement some well-defined, well-sandboxed functionality. Usually, interface has one endpoint, like you have in human interface, because you are sending only the information about mouse movements or keyboard strokes. Or you have 2 endpoints, and one of them is in direction, and the second one is in out direction. So you get the bidirectional communication channel between host and the device. Interfaces are grouped into configurations. Configuration is a group of interfaces which can be used in the same time. It means that all interfaces in active configuration may be used by the host. Single device may have multiple configurations, but only one of them may be active in the same time. Apart from all those endpoints which are grouped into interfaces, we have the special one, the endpoint 0, the mandatory one, which has to be implemented by each device, and it is not grouped into any interface. So it looks quite complicated. So we have to describe it somehow, because our host, when we connect our device, needs to learn about the abilities of that particular device. So each USB word entity is described by a structure called USB descriptor. We have USB device descriptor to describing our device as a whole, configuration descriptor, interface descriptor, and endpoint descriptor. Let's go through the most important fields of those descriptors. First of all, the ID vendor. It's a magic number which you get from the USB organization if you would like to manufacture some USB devices. And of course, it's not free. You have to pay for it. When you buy one ID vendor, you may use all ID products, and they are used to differentiate between products which are not compatible. So if you get your mobile phone, probably most of Samsung phones use the same product ID because they offer the same USB functionalities and they are all backward compatible. So we are not changing the ID product, because your drivers are used to have that ID product, not other one. Then we have information about class. The same information about class is repeated in interface descriptor. It's not really the same. It's the same kind of field. What is class? Well, class is identity of some standard, some well-defined communication protocol. For example, you have the SSH protocol. So a class in terms of USB is a triple which identifies the SSH protocol. So such triple may identify, for example, mass storage protocol. Here is the list of available device classes. You have the audio class, you have communication class, human interface, and of course, vendor-specific. If you see vendor-specific class, it means, well, okay, I don't know nothing. Class information may be used to choose a driver as the vendor information. Then we have some strings, the manufacturer, the string which represents the manufacturer, of course, the product, the serial, and of course number of configuration. Each configuration has information about amount of power which is needed from the host to run this configuration, and the number of interfaces. Each interface has the class information and the string, which can be also used to distinguish between two interfaces. Then we got the endpoint descriptor. We've got the endpoint address, which identifies this particular endpoint, like a port number in TCP. And the attributes which tell us about the type of this endpoint. Is it bulk, is it interrupt, or is it ISO? Okay, so how may we learn what we have really connected? I have here some development board. It's called Odroid. It's pretty the same as Galaxy S3, but in the form of developer board without the screen. I have set up the USB device there using the USB gadget subsystem, and now I will connect this to my computer using the USB, of course, not the Ethernet. Okay, I have connected something. And now I would like to learn what I have really connected. It looks like developer board, so I have no idea what I have connected. First of all, the message. It's always your friend. And we should see it's our device. It says that we have connected new high-speed device, so it's USB 2.0. ID vendor, ID product. The number here we will describe later. Strings. And debugging message about registered driver. Apart from the message, we may get some information from LSUSB.
Can you make this terminal a little bit shorter at the bottom?
Yep.
Thank you.
Okay, so LSUSB, and we should see Samsung. Now, minus file means verbose, minus D, vendor ID and product ID. Okay, and that's the information about our device. Those information comes from USB devices, from USB descriptors in general. If you go through them, you will see that it's generally the same information. We have this ID product, ID vendor, strings, and then configurations. We see here, first configuration, it contains two interfaces. They are both used to implement Ethernet over USB functionality. And in second configuration, we have some mystery vendor-specific interface. But I may tell you that it's the generic serial, so it's really nothing more than sending a raw data from serial port to other serial port over the USB. Okay, so plug and play. As you have seen, I connected this, and it was just working. I don't need to do anything more. So how it happened? First of all, I connected the device. That's the mandatory point. Then my host detected the event of connecting the new device and set some address for it. Got some information from the device descriptors, choose configuration, because there were two configurations were available, and only one of them has been chosen. Then it chose drivers for the interfaces, and I could start using this device. How do we set address? On plugin, each device uses default address 0. Host decides which address should be assigned and simply assigns this address to the device. Usually, addresses on USB bus are simply growing. So this formula is the best description of how do we set address for each new device. Device details, of course, all informations from the descriptors sent by device. And which configuration? It's not so simple, because do we have enough power? We cannot connect many devices to single hub which is not powered. Let's say that you would like to connect 2 USB disks to one USB hub, and the USB hub declares that it needs 500 milliamperes, so the maximum amount, and you would like to connect to this hub 2 USB disks which also would like to take 500 milliamperes. So you have 1 milliampere, and you have here on the other side of the hub you have 500 milliamperes, and how we are going to balance this if hub is not powered? So we need to control this in every point of our USB 3. Some broken devices introduce a configuration without any interface, so we are filtering them usually. And if device has only one configuration, we are done. Just choose the first one. If not, we choose the first configuration, which first interface class is different than vendor specific. Why? Well, the rationale from the Linux kernel says, Linux is not the most popular operating system in the world, yet. So we are more likely to have a generic driver for some well-defined, well-standardized protocol than for some vendor-specific protocol which we don't know. So after choosing the configuration, all interfaces from this configuration becomes available. So it means that in one configuration you may have multiple functionalities, not only one. So in the same time your device may be a pen drive and maybe an Ethernet card. But before it becomes a real functionality, before we can get our network interface, we have to choose a driver for our interfaces. What driver really is? Well, first of all, it's a piece of kernel code. That's obvious. This code is described using struct USB driver, and usually it's nothing more than a translation layer between USB protocol and common protocol used by other kernel subsystem. If you are implementing the network over the USB, you simply need to transfer the generic calls from the network subsystem to protocol on the USB bus, nothing more. So let's say it's a little bit equivalent of SSH client or web browser. It simply implements a protocol like HTTP or SSH or something. How do we choose our driver? Well, in a standard Linux way. It means that kernel has a list of all registered drivers. Each driver has an array of acceptable device identities. So each driver declares, I'm compatible with such device. Choose me for them. Kernel goes through that list, and if some ID from that array matches, it calls driver probe function. If there is no driver, UDIF may load the module. How UDIF may learn which module should be loaded. Each module has a module alias. This alias is generated based on the device ID provided by the driver. So each time when we connect a new device, we are able to recreate the string and then find the module based on information about the device. What kind of information are stored in the device identity? First of all, we have the field match flags. It informs us which field we would like to match against. There are suitable defines. The vendor ID, product ID. This is the pair which is used if we are going to write a driver for some vendor-specific interface. If you would like to implement our driver for some generic protocol, which is standardized, we will use the information from the interface or device class. And some helper for implementing vendor-specific device. You may choose the index of the interface in the configuration. So if your vendor-specific device provides more than one interface, you may choose to which one you would like to bind this driver, to the first one or to the second one or third one. And some field for the driver information are used usually for something which is called quirks. It means bypassing some broken devices or some special behavior for this particular kind of device. Okay, so how does it look on a big picture? We have our device. In this case, it's a Droid, but usually it will be a phone or pen drive or something. We have our host controller, driver for that host controller, USB device. It represents our USB device as a whole. And we have a generic driver for all USB devices. And then we will have USB interfaces and drivers for interfaces. Because USB drivers are probed for USB interfaces, not for the whole device. Each driver provides usually something to user space, let's say a network card, or input source if it's human interface, and simply our user space is using them. That's all. Everything happens automatically. But not always it works perfectly. Automation is really good. It's really something what user like. If he can connect his pen drive and everything is working, he gets a pop-up with pen drive content, it's really great. But it's not working in many cases. First of all, USB is considered now as a security issue because all devices are using automatically. And this is the vulnerability which is being exploited, for example, by the bad USB attack. You connect a pen drive, but this pen drive has a firmware taken from the keyboard, and it starts sending keystrokes to your computer, as like you can do from your own keyboard. On the other hand, you may have combined USB device, which introduces itself as a pen drive and as a keyboard in the same time. So probably you would like to use only the pen drive functionality, but filter out the keyboard part. What if kernel choose wrong configuration? We choose first configuration, which first interface is not vendor specific. And what if I have developed my own device and I really want to use the second configuration, not the first one? Because second configurations give me more possibilities. Then what if we cannot find the driver for this device? You connect your rocket launcher and it's not working because you don't have a device. You don't have a driver. And last but not least, what if wrong driver has been bound to this device? Multiple driver may declare compatibility with the same vendor ID and product ID, or we may need some special handling for this particular vendor ID and product ID pair, not only the class information. We need some methods of changing those assignments. Fortunately, kernel provides quite extensible sysfs infrastructure. It may be used to get information about connected device. It may be used for some device management and drivers information and management. And also provides a device node which can be used to communicate using the USB protocol. Usually you don't want to use this directly, but you would like to use libUSB to talk with your device. Okay, so if you go to sysbus USB devices and then execute ls, you will see a bunch of numbers and a bunch of magic directories. So let's try to demystify them. First of all directories which starts with USB and then has a number represents the host controllers. Single computer, single machine may have multiple USB host controllers. It means multiple independent USB buses. Then we have a directory formed like this. X is the ID of the host controller, which is used for the communication. And then we have physical path to the USB port to which this device is connected. For example, for this printer, we have our host controller. Then we have some hub, which is connected to the third port. Then we have another hub, which is connected to the second port. And then we have our printer, which is connected to the third port. So the name of directory for this printer would be 1 as a bus ID, then 3 as a port number in the top hub, then 2 as another port number, and then 3 as the last one. And that's the unique identity of this device on our machine. There is no other unique identity string other than this. So you may have two totally the same USB devices connected to your computer, but this directory will be always unique because you have to connect it to two different USB ports. The last type of directories is directory which represents USB interface. It starts with USB device identity, and then you have configuration number, the active one, and the interface number from the device, from the interface descriptor. Okay, so what we can do using our sysfs infrastructure? First of all, we may limit the number of allowed devices. So we may say, I don't want any more than one human interface device. Just one keyboard, nothing more. We may use this also to prevent from some kernel ops if we have a driver which we know is vulnerable, and if some device is being connected, it may blow up our computer. We may simply say that we are not authorizing this device for usage. If device is not authorized, it's left in unconfigured state. It means that it's in state 0, configuration has not been chosen, there is no interfaces in sysfs directory, so there is no drivers binding to this device. All that stuff can be automated using the USB Guard project. It's a security project which allows you to filter your USB devices, so you may allow certain groups of devices or anything what you like. How it works under the hood? Well, you go to the directory which represents your USB host controller. You say that, okay, by default, all USB devices are unauthorized. I will do this by myself. When I check this device, I will decide if I would like to use it or not. Then you go to the directory of this particular device and simply authorize it. When you authorize your device, kernel will choose the configuration, create interfaces, and probe drivers for them. The next one. Here we are operating on our device as a whole. But what if you would like to filter part of USB device functionality? we would like to use only one interface out of 3 or maybe 5 in other. Well, it's pretty the same as the device authorization, but now for authorizing the interface, we go to the interface directory, and after authorizing the interface, we have to trigger driver probing for our interface. Why? Well, some functionalities needs more than one interface. So before you start probing a driver for that functionality, you need to authorize both of them. Usage is pretty the same. Choose your USB bus. Now you write 0 to interface authorize default, and you can authorize your individual interfaces and trigger driver probing for that interface. What's the difference? Even if interface authorize default is set to 0, kernel will choose configuration for this device. All interfaces can be found in sysfs, and all interfaces are visible to the kernel. So we authorized some interfaces, we know how to filter them, we know how to filter devices, but what if our kernel choose wrong configuration? We may have multiple configuration and our kernel choose the first one. We just go to the device directory, check current configuration, and simply write to this attribute to set a new one. No rocket science. Okay. So it's really often that some cheap manufacturers simply set random vendor IDs and product IDs. Yeah, you know, you buy a pen drive and it says, oh, I'm manufactured by 12345 and my product ID is 54678. Okay, that's great. But then you buy another one and it say, I'm ABCD and my product number is EFFF because I can. So some manufacturers are doing this, and unfortunately kernel drivers are not always actual or as actual as we need, so they are not probing for that devices. It was the case with, I don't remember, it was a kind of LED display on the USB. On some moment they changed the vendor ID and product ID from one nonsense to another nonsense, but they did this, and you cannot simply fix this on the USB device because you don't have access to the console. So what you need is to add a new device identity to driver which is compatible with this device. How we can do this? There is a functionality called dynamic IDs. You can add any number of additional device identities to each USB driver. There are 3 allowed formats for this. First of all is just the vendor ID and product ID. Second one is the vendor ID, product ID, and the interface class. And the last one is the vendor ID, product ID, interface class, and device information, which is referenced as the vendor ID and product ID. How it works? You remember on the very bottom, you have here the driver information. The information about the quirks, about the spatial behavior of this driver for this particular device. When you are using the last format, you can tell your kernel, okay, I would like to add a new entry to the dynamic IDs and take the driver information from another entry in device ID in that driver. Remember that all numbers which you use here are interpreted as a hex. In contrast, the interface class information in LSUSB is displayed in digital format, in decimal, So you have to be careful, otherwise you will get the invalid value here. Okay, how do we add a new device identity to the driver? You simply go to the directory of the driver, sysbus USB drivers, the driver name, and write to the file called new ID. You can check the list of dynamic IDs that are only dynamic IDs. You cannot check the list of driver IDs declared by driver in the code. So only the dynamic, only the one which you write from the sysfs. And you can remove previously added device ID using the remove ID file. Okay, so that's what you need to do to add a new device ID. And what if you would like to say, okay, kernel, you're smart, but I'm smarter than you, and I would like you to choose this driver, not that one. So you simply can check which driver is currently bound to this interface. You can unbound this driver and simply bind another one. Here we should have bind, not unbind. It's definitely not going to work. Okay, so let's do some stuff with it. First of all, we have to say which directory belongs to our device. We have device. Our device has address bus 3 and device 9. LSUSB -T displays you the physical topology. We have the bus 3 and device 9. So we will have 3.2 directory. 3-devices, of course. 3-2. Okay, that's the directory of my USB device. Now I would like my kernel to switch the configuration. So echo, maybe to see the difference. Now I have the USB 0 interface. When I execute,
could you please move up a little bit?
Yep. No. Better now?
Yes.
Okay. So as you see now, I don't have the USB 0 network interface. So probably I mess up something. But not, it's the behavior I expect here. Because now we are using the second configuration. And in second configuration, we have only one interface, which is vendor-specific class. But I know that this interface provides the generic cellular functionality. Unfortunately, my vendor ID and product ID is not handled by any kernel driver, so I need to force some driver to take care of this vendor ID and product ID. So I'm here in the driver directory. I can simply echo. It doesn't matter. It's the vendor ID. It's the product ID. And it's the interface class. OXFF is the vendor specific class. You can see this over here. Done. If I check my message now, I should see that my driver should bounce to that device. But it didn't. Okay, so that's the USB debugging. You are doing something which should work, but it don't. Too much terminals, too much. Okay, so let's simplify this. Maybe the...
Keep the previous value when you do not specify the interface.
The previous value of configuration?
I have only two fixed values.
Yep.
You keep the previous for the third one.
There's a typo in the vendor ID for 08 for E8.
Yep, that's true.
Many components.
Yeah. Okay. So now it should work, and yep. I have the TTI USB 1 port. So it means that, yeah, we managed to get our serial driver working. That's huge success. Really, believe me. Okay, so what I can do now is, for example, stop authorizing USB interfaces by default. So, I mean, I can just do echo 0 USB free interface authorized default. Okay. No. It should. Okay. Now. Okay. Don't know why. Okay. So, now if I switch configuration of my USB device back to the first one, when we had the network interface, we will simply have nothing, because those new interfaces are not authorized to be used by our kernel. So let's do this. Echo 1. Sorry, no USB 0 interface. And what I can do now is simply echo 1.0 authorized .1 authorized, and now echo -2 1.02, of course, echo -n to do not add the new line character. If config no, please. Okay. And once again, we have the USB 0 network interface. Okay, so we managed to put a driver of our choice on the top of some USB device. So maybe let's start looking at it. Let's start sniffing what he is really doing. First of all, some basics of the USB communication. USB is a host-controlled bus. Nothing on the bus can happen without host first initiating it. It means that your device is not initiating any transfer. As long as you will not ask your device for data, it's not going to send you anything. USB is a pooled bus. It means that your host controller is constantly asking all devices, sending or requesting the data. How USB transfer happen? First of all, we have a transaction. And a transaction is a delivery of single portion of the data of W max packet size is the value declared in endpoint descriptor. And set of transaction from which only the last one is a short transaction or zero length transaction is called a transfer. So it's USB transfer. And usually in drivers we operate on a transfer level. We don't care about transaction. This is the role of the host controller to split our transfer into transaction. We are operating on USB transfers. USB request block is a base kernel abstraction entity which is usually one-to-one matched with transfer. Of course, there are tricks where you can do that multiple URB will be put into one transfer, but not many driver does it. Usually it's a single USB transaction. API, which is used to send this, is asynchronous, and all drivers in kernel are using the USB devices in asynchronous mode. And URB is really a kind of envelope for the USB data. It doesn't care what you are going to send. We are simply giving the data and sending it to some particular endpoint. So what do we have inside our URB? Of course, there are small fields. I have cut this. Only the most important are here. Some handler to put this on the list. This belongs to the owner of this structure. USB device, because we have to identify where we are going to send this. And of course, the port number. Then we have the status. Status is a field which should be checked in a completion routine. Completion is a callback which you will get when this transfer is ready. You should check this field, and you should check the actual length. Because transfer may end up in an error, but part of the data may have been already sent. So we should check how much data has been already sent and how much data is left. What you are going to do with this data, it depends on your protocol which you are implementing. Okay. So we say the transfer buffer, of course, the data which we are going to send. And if you are using the control transfer, you have to point out the setup package, because control transfer consists of two stages. In one, we are sending 4 integers to the device, and in second one, we are sending a data, or we are getting the data from the device. So the typical USB driver, how does it look? Well, generally, from the USB point of view, we don't have much to do. We have the probe function, which should check the device and allocate all required resources. We have the disconnect for cleanup. We have the completion routine for our URBs, which we are using. And the rest of the driver is related to the subsystem, which we use to provide some functionality to the user. Typical bugs. Missing descriptors. Many drivers try to get some descriptor from the device and simply assume that device will provide it. Sorry, your device are not as good as you think so. They are going to return errors. They are going to return less data than you expect. They are going to do any sick things. You should always check. If you are submitting a transfer, if you try to get some descriptor from the device, you should always check if it is valid. Then, you should check if interface contains as much endpoints as you expect. If you expect 2 endpoints, you should never try to get endpoint and then don't check the results. Because kernel may return null. And we have null pointer the reference because I have connected some broken device. There is no error handling in complete routine. This point is usually a problem if you are running some automated testing laboratory using the USB. Well, if you are doing so, then Well, I don't know what to say, but you are not going to sleep well. Because USB and running some automated system on the top of USB is really asking for problems. There are some bugs in completion which are not being checked in many completion routines, which are really rare, and most of the users don't face them. Because how long are you using your pen drive? 5 minutes, 10 minutes, half an hour? And such automated testing laboratory is running for a month. Oh, no, sorry, it's running for a day. Then it's simply sending an errors from the USB, nothing more. In the end, device sometimes gets broken, something gets wrong, and sends some malformed packages. You are communicating with the device using some defined protocol, and this protocol may sometimes mess up. You should always handle the errors which are related to your specs. And many drivers simply implement the things which are usually working and don't care about the error situation, about the error handling. There are, of course, some hardware USB sniffers. The one from Elysis, I have one of those analyzers on my desk. It's really good, but it's really pricey. It can show you and dissect most of USB protocols, most of standard protocols. So if you are going to debug some network card, some pen drive, it can dissect all the classes and that kind of stuff. You can also add your own one. Beagle can the same. So they are pretty much the same. They are going also to show you the physical layer, how your transfer is split into transaction, how the transaction happens, the electrical level of the USB protocol. The next one is the open hardware USB sniffer. I heard about it. It's called OpenVis SLA. I heard that people are using it. I'm really, really excited to build my own one, but I'm not sure if it's really working. If there is someone who used this, I will be happy to chat and talk about this and maybe order some parts together. And because, you know, the difference in price, I can buy 10 of them for one analyzer.
Is the other one working, in your opinion, the hardware sniffers in general?
Yep, hardware sniffers are working, definitely. They are really good. They are really good, but they are really pricey. So the problem is the price.
What else can you do besides sniffing? Let's say what more you do with them rather than with the Linux kernel?
Okay, so what you can do more? You can do some electrical level sniffing. You can check the states, the J and K states, the timing information is really... Well, try to analyze USB 3.0 using the logical analyzer. Okay, so I don't have such good logic analyzer to analyze even 2.0. So,
that's why that works.
Yeah. Okay, so that's the hardware part. But our Linux kernel has some basic sniffing functionality which can be used to sniff a traffic between drivers and devices. It's called the USB monitor. It's simply nothing more than a logging system for USB request blocks. Each time when driver tries to send something, it calls submit. It means pass this to the host controller and try to send this to the device. And we are simply logging it. Each time when transfer is finished, we get the completion routine. So we are simply logging it. Each time when we try to submit and we end up in an error, we are also logging this event. We have two formats available, the text one and the binary one. It's simply a character device from which you can read the binary data about your USB transfer. When you load the USB mon module, you will get one instance of the USB mon device per each USB bus. Okay, where you should look for the data. If you would like to see what your driver is sending, you should not look in the completion. Why? When you open your logs from the USB monitor, you will see two kinds of information usually. The information about URB submit and URB complete. If your driver is sending the data, in URB complete you may have nothing. In URB submit, you have the whole buffer which is important to you. If your driver is waiting for data, then there is no point in checking the buffer on the URB submit, because there is rubbish, nothing more than rubbish. Okay, so using the raw USB mon interface is really not a thing which you want to do, so just go ahead and use Wireshark. Okay, so let's catch something. Okay, so we would like to monitor okay, if you don't want to be polished.
I think we might have to skip this last demo.
Okay. So sorry, we don't have time. That's the other bus. It's something which you are going to see when you open Wireshark, all the dissectors for most common USB protocols like mass storage or something, so we'll get the higher level of the communication. Okay, so that's all from me. Thank you very much for attending. If you have some questions,